Hey y'all. All right, this is a solution for the matrix multiply exercise from the first storage lecture. Recall the point of the matrix multiply exercise is to make a matrix multiply function run faster. In our handout code, that we have a fast matrix multiply function and a base matrix multiply function. They're both about the same. And they're both exactly the same in terms of code. They take about the same amount of time to run because of variability. They're not exactly the same, of course. For instance, in this case, the fast matrix multiplication, which is literally the same code as the base, ran about 1% slower. If we run it again, we'll see a different ratio. Fast and base both take around 10 seconds to multiply 2,000 by 1,000 matrices into a third 1,000 by 1,000 matrix. So, let's just solve this problem as quickly as we can. We'll load up the fast matrix multiply function and then just move one line of code, maybe one line up. So rather than multiply rather than iterate over the matrix in order I, j, k, we iterate in the order I, k, j. Make and run matrix multiply. And presto changeo, we will see that matrix multiply is now running at around 7% of the time. It's running, 7.07x the time of the base matrix multiply. So it's running roughly 20 times faster. Just to speed up this video, we'll run it a couple more times, but this time I'm going to tell it not to run the base. I'm going to tell it to assume that the base took about 9.05 seconds, which is roughly what we've seen. So we can see that it's running basically 0.06, 0.07 times every time. Thank you for watching. That's the end. That's not the end. We have to explain why this simple trick worked as well as it did. Okay. So let's take a look back again at the matrix multiply function. First question. Why is it valid to change the order of these loops? Well, let's first think about what the loops are doing. Recall that in a matrix multiplication, we have three matrices. In our code, they're all square, but here they're slightly different sizes. And the way that a matrix multiplication works in the abstract is that a given cell of the output matrix, here cell I, comma j, in the ith row in the jth column, is computed by pairwise multiplying the elements in the ith column of the left-hand matrix, and the ith row of the left-hand matrix, and the jth column of the right-hand operand. So, and then summing the results. So, in the left-hand matrix, we do A bracket I bracket 0 times B bracket 0 bracket j. Notice the way that j is a column and I is a row everywhere it appears. So we do those plus A bracket I bracket 1 times B bracket 1 bracket j plus A bracket I bracket 2 times B bracket 2 bracket j. So you can see that we're just sort of summing up these pairwise products of the scalar elements of the matrix. And we need to do that computation once per cell of the output. So if we look at these series of loops, I and j are the row and column of the output. This is the output matrix C. And then k is this inner loop that goes over the columns of the left-hand operand and the rows of the right-hand operand and disappears from the result. Okay? So we need three loops. That makes this an n cubed algorithm since size, or n, is the same in all three loops. Now, are these loops dependent on one another? Is there any sense in which the order of the loop matters? The answer there is no. We can tell that that a loop order matters if we would compute a different result when we change the order of the loops. Will we perform a different result here? No, because in each case, the loops themselves don't depend on each other. Here, this loop will run for size times, no matter whether it's the outermost loop or the innermost loop. It always runs for size times. The computation of the first index and the next index and the bound index don't depend on its placement inside of I. Similarly, no matter what order we choose for these additions, for the way that we're computing the output element of the matrix, all of these computations are commutative. We're adding a bunch of products, and addition is commutative. Those of you who know something about floating point arithmetic will know that addition is not actually completely commutative when we add floating point numbers, but we'll wave that away for now. So given that these computations, so if we unrolled these loops, for example, for a 2x2 matrix, which is a pretty simple matrix, what we'll see is something like this. The first time through the loop, we will add to the 0,0th element of the output matrix, the result matrix, the product of the 0,0th elements of both input matrices. Okay? So I is 0, j is 0, k is 0. So this is an example when size equals 2. Okay, the next thing we do is we increment k by 1. That increments the column number in A and the row number in B. The next thing we do is we increment k one more time. Now k is equal to size. So we reset k and increment j instead. So that will increment j, which is the column number of the output. It doesn't increment, now A returns to 0, 0 because k is now 0. And in B, we take j as 1 and k is 0. Increment k by 1. That increments the column number on A, the row number on B. You can see how this goes. The next time through, we increment I. And that changes the row number on A, and it changes nothing on B, because I doesn't occur in the computation of the element of B that we compute. Now, if you look at these, because addition is commutative, no matter what order we perform these in, we could perform them in a completely random order. And as long as we could do each addition exactly once, we'll compute the same result. The answers in C will be the same. So that says that we can reorder these loops however we want. So if we want to reorder the loops, you might try all 6 orders. There are 6 total orders. For instance, what if we put I in the innermost place? So rather than ijk, we're incrementing jki. How will that perform? It does not perform well. In fact, it performs worse than the original order. We'll see that shortly, or I guess we'll see that longly, because I would expect this to take around 20 seconds to compute. Thinking. Yep, took 24.6 seconds. That's 2.7 times worse than the input. So I in the innermost place is not good. K in the innermost place is where we started. What about J in the innermost place? Well, J in the innermost place is very fast. Why is this? To understand, it's best if we take a step back and think pictorially. So remember, this is not only a picture of the abstract definition of matrix multiplication, it is also a picture of the values in the matrices that are accessed during a complete run through the innermost loop when k is innermost. So that's this order. We do I and then j and then k. This picture is the same if we do j and then I and then k. So what I mean by this is every cell accessed in that loop is now highlighted for every value of k. K equals 0 is that cell, and also that cell of the result matrix is accessed. When k equals 1, we access that cell of A, that cell of B, and again, we access the same cell of the output matrix. Okay? So every value of k is highlighted in this diagram, and that says that these are the memory locations accessed for each ij pair, for an entire run of the innermost k loop. Make sense? Notice that we have one horizontal line, one vertical line, and one point. What happens if we run j as the innermost loop? Okay, so what we would expect is we would expect this j column to disappear from the system, from our diagram, because j is no longer fixed. Here's what that looks like. So now that j is the innermost loop, we access every j value on the output matrix, the result matrix, so j equals 0, j equals 1, j equals 2, j equals 3, and so forth. We access every j index in the B matrix, the right-hand operand, j equals 0 through j equals n. However, for the A matrix, we access only a single point, the point at I, k. That's the left-hand operand. So you can see this if we look at these arguments. So j is the innermost matrix, the innermost index, excuse me. So C uses j as a column, so we're going to access an entire row in C. B uses j as a column, so we're going to access an entire row in B. A doesn't access j at all, so we're going to access a single point in A. Okay, so now, rather than a horizontal line and a vertical line, we're accessing two horizontal lines. What about our bad order? And again, this picture is the same if we do kij or ikj. Our bad order is where I is the innermost loop. kji, jki. So if I is the innermost loop, let's just reason about this without looking at the picture first. There's going to be a single point in B that we access because I doesn't appear in its arguments. We're going to access an entire column of A, the left-hand operand, because I goes through all possible values. And we're going to access an entire column of C, the result matrix, because again, I goes through all possible operands. And in fact, that's what we'll see. This is how that looks pictorially. Two vertical lines and a point. How does this correspond to the cache? Well, the way that these matrices are laid out in memory is in row major order. We can tell that by looking at this function. Okay, so the row number is multiplied by the size when we access the array of doubles that contains the matrix data. Then we add the column. So what that means is that the cache lines of data stored in these matrices are laid out like this. So a single double is only 8 bytes. A cache line is at least 64 bytes. So a cache line in one of these matrices is going to contain multiple columns in a single row. That's why I've drawn the cache lines here like bricks that are sort of longer than they are tall. So that means that if we access one element, one column, then we go to the adjacent column in the same row, we're quite likely to hit the same cache line. And what that means is that our good order accesses many fewer cache lines than our bad order. Let's take a look. This is the original order. So we access a single cache line in C. We access a relatively small number of cache lines in A, but we access one cache line per row in B. In our 1,000 by 1,000 matrix, this is going to be one cache line in C plus roughly 125 cache lines in B. That's 1,000 divided by 8, plus 1,000 cache lines in B. So, sorry, 125 in A, 1,000 in B, 1 in C. Okay, so 1,000, 126 cache lines. In our good order, we're going to access one cache line in A, 125 in B, and 125 in C. So that's just 251 cache lines. That's roughly a quarter of the number of cache lines as the initial order. And in our bad order, we're accessing 1,000 cache lines in A, 1 in B, and 1,000 in C. So that's 2,001 cache lines. That's roughly twice as bad, which is what we saw. We saw a result that was roughly twice as slow as the original order. So hopefully this picture and this reasoning will help you see how we can, just by changing the order that we perform some computations, really make the system run much, much faster. Is this the only way to do this problem? No, it's not. Another way that we could do this problem is by transforming the B matrix so that it was not in row major order, but was in column major order. So here's the way that that might work. So in each case, we're going to transpose B. And I'm going to do this, I really should transpose B back again, but I'm not going to bother. So for each row, we go through the triangular matrix, the upper triangular matrix that has or the lower triangular matrix, excuse me, that has smaller number columns. So size tj equals 0, j is less than I plus j. We swap the value in the lower triangular matrix with the value in the upper triangular matrix. So double temp equals star me b size ij. Star me b size ij equals star me b size ji. And then star me b size ji equals temp. We've now we've transposed the matrix. And what that means is that in our original order, we would swap the order of arguments for accessing B. Now check this out. Since we swapped those arguments, we're now back to this picture, where we're accessing, well, we're back into it's not exactly this picture, but we've got two horizontal lines plus one point. But in this case, the point is in C, and the horizontal lines are in A and B, because in both A and B, we're modifying the column in the innermost loop. Let's see how that performs. We should expect it to perform. It's not bad. It's not bad. It's not as good as our best order of switching loops, because we have to do the additional work of transposing the matrix. But in fact, we did see some people who transposed the matrix in class, and it's not a bad solution. But there is even a better solution. So let's say that just for the sake of argument, you were like, you know, maybe people know how to multiply matrices. Maybe that's an important operation. So we could, maybe somebody has written a library for us that could do a good job of multiplying matrices together. Let's see, fast matrix multiply C language. Optimize matrix multiplication in C. How to optimize matrix multiplication operation. Oh boy, there's a lot of good. BLAST 3 compatible fast matrix multiply. BLAST. I wonder what that is. Well, let's add another search term. We're looking for a library that'll let us do this. C libraries for mathematical matrix operations. There's a bunch of interesting libraries here. Basic linear algebra subprograms. rather than go through the steps that I took to actually find our fast matrix multiplication, I'm just going to show you what it is. In wickedmatrixmultiply.c, we include a library header file that implements fast matrix multiplication, and here's how we actually multiply the matrices together. So cblast dgem, what a name. cblast dgem is a function for multiplying matrices together that performs this computation. So alpha times A times B plus beta times the result matrix. So there's beta. What we're saying is, don't consider the existing contents of C. Multiply A by 1. Multiply it by B. So these arguments say that the matrices are stored in row major order. Neither of them is transposed. And these are the size arguments. Since they're all square, we pass in size for the same argument every time. Okay, understanding all of these arguments is outside the scope, but it's not too bad. If we look at how fast wicked matrix multiply performs, wicked matrix multiply performs far faster than our magical sort of the indexes. However, there is a cost that we pay, which is precision. Wicked matrix multiply doesn't give us the exact same result. It's very close. It's only like 10 to the minus 13th percent off. So like off by by a multiplicative factor of 10 to the minus 15. That is unlikely to matter for anybody. What we see if we look at the hexadecimal versions of these floating point constants is that usually the last two hexadecimal places are off by a little tiny bit. Okay, so we're paying something in precision for this very fast multiplier. How fast is it? So remember that the fastest we got was 0.06x. We're now down more than a factor of 10 faster to 0.004x. The way that this works is that cblast is using some special instructions built into recent processors that actually know how to multiply many numbers together at the same time. So rather than loading separate scalars and multiplying them, it loads multiple scalars at once and then multiplies them as a unit. It also may be doing some precision tightening, so it's not worrying about the lower order bits of the result. That's why the result is off. So the lessons of this: first, think about the cache. Second, look for libraries if you're doing something sort of foundational. Thanks for watching.